Uh, so good morning to everyone. We are really pleased to have yet another, you know, online seminar, webinar, and I think today's topic is really interesting, and it is going to be, presented by Dr. Ellie Fini from um, Arizona State University. She is a Fulbright scholar of Aalborg University of Denmark. Also, she has extensive track record in working on sustainability area. So today's, and I have had the opportunity to actually know Ellie, for quite some time, and I follow her work, pretty closely, and she always has some interesting and some innovative ideas. So today she's going to talk about actually some type of a carbon neutral or maybe uh, carbon negative type of topic. It is a very interesting topic in the materials area. Before I actually ask her to make the presentation, I just wanted to let the group know that you can actually get a 1 hour PDH, for joining this event. So if you, when you signed in, if you indicated that, then Ellen would be, sending you the PDH. Also, the way we are going to do it is that if you have questions, you can ask. We're going to hold the questions till our presentation is over, and then either you can raise hand and ask questions, or you could also send a message to me, Musharraf Zaman, through the chat box. So either through the chat box, and we'll look into those questions at the end, and or you could actually raise hand and ask your questions at the end. I want to thank our SPTC staff, specifically Alan Leon and Dr. Michael Molina, for their assistance in making this event possible. Dr. Fini was supposed to be actually giving a hybrid event, so some of us would be able to see her, but in the last minute, I think she has had some issues, so she could not be here in person. But nonetheless, we look forward to listening to her presentation. So with that, I'm going to give the platform to you, Ellie, for your presentation.
Thank you so much, Musharraf, for introduction and for having this talk. Hello, everyone. I guess good morning, good afternoon. If you are in different places with virtual, we don't know where the audience are sitting. So wherever you are, hopefully this talk will give you some ideas about where we're heading in terms of environmental sustainability. As Musharraf mentioned, I'm in Arizona State University, and here we're having one of our research trusts as carbon negative. You may have heard about sustainability, carbon neutral, let's reduce CO2. Here we are pushing toward carbon negative. So I'm going to tell you a bit about what it is and what we want to do with carbon negative approach, which seems catchy to begin with. You know, if you think about, we can actually make the pavement be carbon negative. That's quite a long way. That's why I said towards. So we're just towards carbon negative. So don't expect too much. But we're talking about going toward carbon negative built environment. And here I'm talking about asphalt. I've been working on asphalt for as long as I remember, since my bachelor and graduate college, and now as a faculty. So that's my passion. I tell my student, if you get to asphalt, it's so sticky, you can't leave and go to another area. This is the way to stay. So working on asphalt, you look at this black guy behind me, this whole beautiful black road is actually, think of it is asphalt binder or bitumen. Different people have different naming for it, but it has almost 80% carbon inside that bitumen. So keep that in mind as we go through this talk. We talk about sustainability being having these three pies, three sections of the pie, which is social, environmental, economic aspects. Those have to be all met to have a sustainable project, sustainable built environment. But now we're trying to go a bit further and even go to our carbon negative, which means our roads could actually complement the role of a tree. You may think I'm crazy, you know, that trees are sitting out there absorbing, getting all the CO2 that we breathe. So as I speak to you and you guys sitting listening to me, you are actually emitting CO2, right? So we take oxygen in and we send out all this CO2, which you think about it, all the humans combined, they generate 3 billion tons of CO2 annually. You may think that's a lot, but let me show you what is actually a lot. That's not much. And when you think about what we release as CO2, this is actually the glucose combined with oxygen, which release CO2. So it is really the CO2 that plants or whatever we eat, at some point they absorb. So we can consider ourselves CO2 neutral as human because we release whatever that food and plants that we eat, they have sequestered sort of. So we just give back the same amount. But think about where the CO2s are and the carbon. So you have heard, I'm sure, about climate change and the temperature going up, the polar bears are dying, all those things that associated with CO2 and greenhouse gases, methane being even 21 times worse than CO2 in global warming. But all those have to do with carbon as an atom inside those, right? CO2 is carbon and oxygen. So we're talking carbon. Look at this graph, and I'm not going to talk about too much atmosphere. It's not my expertise, but this graph will give you a good picture of where the current carbons are. If you look at those numbers in parentheses, you can see, for instance, here in the corner is soil, 2,300, here deep ocean, 37,000. Those in parentheses means carbon that are already stored. So if you don't touch them, they are there, they remain. But if you, of course, start digging up, for instance, this fossil fuel pool, look at it in the bottom here, 10,000. If I start digging it up and bring it up burning, so then I can release it. But right now it's sitting there. Look at the numbers on the top here, for instance, you can see the atmosphere has 800 in it. And photosynthesis is the yellow numbers shows the active numbers. So photosynthesis annually get 120 in, which is trees and plants, which they convert CO2, right, to starch, to greens that you see. So those conversion is 120, and the red one is actually man-made contribution, whether it's positive or negative. Here we can put number 3 as human contribution to CO2 adding to this number. Here, look at the ocean. There are 90 from the ocean itself that absorb from the air. You may say, well, how does the ocean get the CO2? Well, CO2 actually is soluble in water. That's how the water becomes more acidic as the CO2 gets in. Also, we have phytoplankton and all those, marine creatures that makes exoskeleton. So those are like, think of it, seashells. Seashells is getting CO2 and converted to minerals. So that's another way for ocean to help, which is 90. So if ocean left alone, it takes 90 and it gives out 90. You can see these 2 arrows, so they're good. But then when we contribute, we come in, we actually add another 2, which goes to the ocean. That's how it may become more acidic, and that's called acidification. So the red numbers are the one that human sort of manipulates and contributes somehow. You look at this 9 here, that's the largest number. Fossil fuel, cement, land use, and our roads, asphalt road, is some, we like to think is a tiny part of that number, but that's right there. Some of those CO2 that comes from man-made activities, land use change, cement and construction and all this thing. So to summarize this figure, all these numbers, white ones and yellow ones is fine, but look at the red ones. If you sum them up, you have 9 from fossil fuel comes out as or cement production, construction, asphalt production, and then two units of it goes to the ocean, which is not good. It makes it more acidic, but anyway, it goes away. And then 3 units goes through photosynthesis. So here we end up with a surplus of 4. So 9 minus 3 minus 2 end up with a surplus of 4. And that's how we say, well, watch, there is more CO2 coming up, the climate is getting warmer, whatever. This is the budget that we have to manage, the 4, if we can now get rid of it. So when I think about carbon negative, I'm thinking of, or I'm talking about getting those carbon from the air and hide it in your pocket. Somehow sequester it somewhere. Can I take away from those 4, which is surplus? And hopefully at some point, even this 2, I want to get it and sequester it somewhere so it doesn't make the ocean more acidic, which is not good for marines and, creature living there and so forth. So let's think about this 4 and think about carbon negative. If I can start collecting those 4 and sequester it somewhere, then I'm helping. At least I'm kind of subsidizing some of the things that are released somewhere else. So if you ever in Phoenix, in Arizona State University, we have this mechanical tree, which is standing in the middle of campus and collecting CO2 from the air. We then put them in capsules, large containers, and then we take those CO2 we collected directly from the air into those containers. We feed them to algae in our algae pool, and then we make algae. So then some of this stuff, or biomass, we make other biomass that are quick turnaround. So if you think about trees here in this picture, they're good, but they're long turnaround. It takes time for the tree to grow up and to become mature, and then you cut it and maybe put it in the timber, which then end up in your building. Is good. It's a still sequestration, but it's a long term. So we're looking at quick turnaround shrubs, hemp, biomass, bamboos, others that are quicker, and algae, which is the extreme quickest we can control and get it fast. So CO2 from air, this CO2 right here, can turn to biomass, such as algae. And that's how I'm cleaning up. So Klaus, my colleague who actually led that mechanical tree, is talking about if we can clean up air in Arizona, they can still emit somewhere in Massachusetts. Is the air, it moves, right? So if I can clean in a corner in one state, like in Oklahoma, in Norman, it's fine. We can help still at other places that are emitting. So let's go to pavement. How we are doing on carbon side. Do we even generate carbon? Where is the carbon? What can we contribute? Well, we do. When you think about every aspect of construction, material sequestering, bringing material from quarry or Mother Nature, think about bitumen. All those materials to come to become a lane mile of pavement, they have energy associated with that, which is actually equivalent. Every lane mile of road is equivalent to 41 US household energy usage. So you can think of how much carbon associated with that. As far as CO2 emission, every lane mile of road pavement is equivalent to 20 US household CO2 emission. So yes, our operation, construction, maintenance of road, it contributes to CO2, which CO2 is carbon, so we are contributing to carbon. And when you think about a mile, okay, well, 20 US household, that's not much. But we don't have just 1 mile, right? We don't have 1 lane mile. We have 4 million miles of road, which majority of those are paved, and they are maintained and go through rehabilitation regularly. We usually have 70% of $100 billion roadway expenditure goes to these activities. So dollar-wise, you can see the contribution. And of course, those dollars goes to construction, turn to that energy and CO2 I just showed you. So yes, we do have a significant contribution to make toward those carbon negative. And if you think about the roads now for a second, just thinking loud, if the roads sitting out there, now they are complementing the trees. if our roads can start actively or passively collect the CO2 from the air, or we collect CO2 like Klaus does with mechanical tree and convert it to a material that then goes to pavement, we can sequester those carbon in pavement for many years. And of course, we do recycling, so this keep going back to pavement as we recycle. So this is just a breakdown of material, construction, transportation, maintenance, as it comes to CO2 and energy. So I put material in red because first, material is my passion, and it has the highest contribution, as you can see. So when you think about material, well, it just doesn't fall from the tree, right? You don't get the bitumen growing on the tree. You actually dig it. You bring the crude oil and then you refine it. You get the bitumen finally, at the bottom of the barrel. All those material production steps needs energy and has CO2 associated with that. So 75% of the whole thing, the whole CO2 I just told you about, is actually associated to material production. So if we wait a second on this slide and think about, if I want to get the most for the buck, for the most for my effort, where would I put it? Well, if you produce the material once, you better make the best use of it, or maybe don't ever throw it out. If you think about asphalt, can we not ever dig it out? Can we not ever throw it out in a pile of wrap or disposed material? Those materials are significant. They've been through a lot of contribute a lot of CO2, so let's make them not go away, at least. And this has been a long journey for asphalt industry. I'm sure many of you know we came a long way from Marshall to Super Pave. This is all attempt to make more durable, longer lasting roads, more sustainable roads. Now we have all the warm mix technologies, which is reducing temperature and fuel consumption and so forth. More recently, balanced mix design is trying to improve the durability and get the rotting and fatigue addressed. So we are making baby steps, I guess, toward the more durable, more sustainable roads. But when we think about material side, if I show you all the carbon that is inside asphalt, think of those. This carbon right now is coming from Mother Earth. Those are the numbers that were sequestered. If we didn't touch them, they were already there. So we dig them up. We put them now into use. If we could get those carbon from the air, those CO2 I showed you, the 4 surplus, and bring them into asphalt, we can talk about now carbon negative, because we are not digging up carbon which is already sitting under the ground. We are getting the carbon from the air. So speaking of this beauty, this is our asphalt. We drive on it. This is what is familiar to all of us. If you look at this, we are very simple. We're not rocket science. Look at this. It's a stone and the glue put together, nice, and give you that smooth road and safe drive. This material right there have carbon associated with it. Whether you dig those quarry to cut these stones to this shape and size, or you got those bitumen, the black ones from the Mother Earth, you made carbon on the way. You release CO2 on the way. I'm gonna dig a bit deeper into the black guy, which is right there as the binder. This is the guy, right? We're all familiar with it. There's a viscous, sticky, gooey, black elements that comes from crude oil. Everybody knows we get crude oil, we break it down to gasoline, jet fuel, all the goodies. And then at the end, we get a bit of asphalt left, which some people call it bottom of the barrel or residue from the refinery. Whatever is coming from the ground, right? Those are the carbon underneath, they were sequestered. So that 3% is what is our share, our industry's share from those. So those asphalt goes to that beautiful mixture, gives us asphalt composite. So if you think about that asphalt, the black one, you just see black right there. But what is this one? If you think about it from molecular side, from carbon size, from what is made this, is actually Mother Earth made it, right? For millions of years under the ground. So those phytoplankton and all those marines and biomass I mentioned, if they go under pressure under the ground for many, many years, they become this crude oil. But we don't have millions of years to wait for the carbon to turn to phytoplankton and phytoplankton to be under pressure to become crude oil. We need a quick turnaround of CO2. So yes, these are organic carbon, which are from phytoplankton or other biomass that turn to this. So this is organic carbon, but it was underground already. We dig it up. Instead of waiting for this, can we dig up carbon from the atmosphere and make this and put it into this, which then we are helping as carbon negative. So I'm going to show you some carbon. I keep talking about carbon. So these are some of the biomass we can grow very quickly and turn them to carbon. The first one is corn stover, switchgrass, miscanthus, algae, woodplant, all of those biomass. But don't worry about which biomass is, but look at the carbon here. They have 77 or 60 to 70% almost carbon in all of those. But of course, I'm talking about elemental carbon, atom carbon here. What is the carbon in asphalt? I can't just directly get this carbon and say I have asphalt. The carbon in asphalt is in aromatics and saturates and this and that, right? We have different compounds. So I actually published this paper recently in, just came out, I guess, a few months ago. It's talking about these carbons being very high in biomass, which biomass, as I mentioned, got the CO2 from the air, photosynthesis become carbon. So remember, these are the short-term carbon collected from the air. So if I can feed those carbon into asphalt, then I can make it. So think of asphalt, the black gooey stuff I just showed you, this guy, if I break it into his components, I see black, just black here. But if I break it into its component, I'm gonna get this 14. And this is how we use solvent separation. Many of you are familiar with what asphalt is made of. The name of asphalt actually comes from asphaltene, which is the most dominant, largest molecules of asphalt. We also have maltane categories, so asphaltene and maltane together makes asphalt. But if you go a bit deeper to see what each of this is, it's just a name, but we can break maltane to resins, polar aromatics, and saturates and naphthalene aromatics. And here in the bottle, I should put the picture here from the lab. You can see this little one on the all the way to the left is asphaltene. Then we have the saturates here, the clear one. We have naphthalene aromatics, non-polar, and polar aromatics, the last one. So these are, when they are mixed, they become that same asphalt. When you separate them, they become this. So not every element of it, as you see, is black. Like saturate is actually quite clear, or this one is quite yellow. So the whole thing is asphalt. So when I talk about carbons, carbons are in these elements. They're embedded in these molecules. If you think about that, the polarity of them, asphaltene has the highest polarity, followed by resin, followed by aromatics, and then finally saturates. Why I am showing you the polarity? Because the more polarizable material is more prone to oxidation. And why I'm talking about oxidation? Because oxidation is causing aging, which we don't want to happen. Remember I said, what if our asphalt never go away? What if we never have to repair a road or never have a pothole? Well, the reason we do have pothole, the reason we have to dig it up, mill it, and dump it or dispose it is because it gets worse and worse with aging. Part of aging is oxidation. I'm showing you the elements of asphalt here. The same thing as showed saturate, aromatic, resin, and asphalt. Then you see in the table. As I keep aging it, and of course, these are accelerated aging in the lab, which are supposed to correlate somehow to the field, but that's still a discussion, separate discussion. But think of it as a progressive aging. On age, brand new from the refinery, I have 12% saturate, 19% asphaltene, and so forth, 15% resin, whatever. As you age it, 2 PAV, that's like a significant amount of age right there. But let's go to the third cycle, 3 PAV. PAV is pressure aging vessel. So you put the sample in there under pressure and temperature, you age it. So as we go through 3, 5, 6, 7, that means longer and longer aging time. You can see the material changing, saturate become 2, asphalting become 29. You can see the change. So chemical composition, a structure of the bitumen asphalt is changing as it goes through aging. So yes, we know based on the pothole appearance that aging is bad. We don't want aged material because the brand new asphalt, it looks beautiful, and the very aged asphalt, it looks full of crack and potholes. So intuitively we say aging is bad. Look at what happened to our roads. And here in chemistry side, you can see also how it changed our roads, our material. So what if I can prevent this? What if I can reverse it? So two solutions, right? I'm going to talk about one solution is stop it, prevent aging, do something that this change doesn't happen. That's number one. The second one, if it happened, reverse it. Sort of, I always tell my students about reversing it as sort of, all those creams and rejuvenator, expensive, pharmaceutical stuff we get put on our skin to look nicer, look cleaner. That's sort of reversing aging. But we can also use preventive methods to prevent aging. So this solution, two solutions maybe help us to keep our material for a longer period. We already put all the CO2 and energy to make them, so we want to keep them as long as possible. So here on the figure on the top, I'm just showing you the aging doesn't impact all those components the same way. We may think that asphalting and saturate, everything would age the same pattern. It doesn't. Look at this one. The total asphalt is on the bottom figure. As I go through the PAV, the y-axis is UV adsorption. So think of it as an indicator. I'm just using UV adsorption as indicator to see how the evolution happens. For the total binder, it goes up and down. For the asphalting alone, it goes down and up. So asphalting and the total binder, they're not going through the same evolution. Just keep that in mind. So I want to show you this one as well, that you may think of aging as oxidation. Yes, that's the dominant effects of aging, but it's not the only thing. And I'm showing you this figure to show how from 0-hour aging to 400 aging, the shape or surface of material under optical change. So it looked like this, and after 400, look like this. So the shape is changing. And then I measure the film thickness. So I have a bitumen thickness. I'm just aging it, and I keep looking at the thickness. Look at the thickness of this from thickness-wise. As the aging progress with hours, it's going down, 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 down to this. So I'm losing something, right? When the material gets thinner and thinner and thinner, what's happening? Some of the molecules are leaving, right? That's how the thickness is reduced. I used to have 600, and now I have 100 on the y-axis. So I lost almost 500. They're gone. And that's the material that is lost to the air. Do we want them to go to the air? No, they don't belong to the air. We put them in asphalt to do something. They have a role, so they better stay there. We don't want to lose them. But the aging actually is a very complex dynamics, but oxidation, and now I'm showing you loss of material, which is not good for us as pavement engineers. We want them not to lose material. It's not good for air quality and people who are breathing it. If I'm losing some of this material to the air, and some are not as healthy, I guess none of them are healthy, but anyway, you don't want to breathe benzene, do you? So if these are the molecules going to the air, or phenols or alkane, they don't belong there. So we don't want that to happen either. So let's talk about solution number one. Well, let's stop it. Let's prevent aging. Let's not any of this happen. But can we do it? So I'm showing you this picture of unaged bitumen and aged bitumen. Everybody, I guess, familiar with this. That's how the aging happens. But this is the picture you get as the aging progress. On the picture, you see all those tiny cracks, looks, changes, whatever. But in the chemistry and the molecules, what happened, or the rheology, what happened. So here on the left, we have carbonyl index. which is basically an indicator of oxidation. When oxygen bonds to our asphalt molecules, we get carbonyl formation. So as the carbonyl, the black line is Arizona asphalt. So black line shows carbonyl goes up, 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 and then still up, but slowly up. So initially very rapidly and then slow down. Here, corresponding to that crossover modulus, which is another rheology-based indicator, as the material age, our crossover modulus goes down, 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 and you can see how it drops. Both curve plots are an indicator of aging. Don't worry about what is on the vertical axis as the indicators. It just shows you it's changing, right? Over the x-axis is time. So I'm just showing you how the asphalt changes in certain properties. And then what we have done, we added some functionalized carbon here, which is made from algae. And you can see the green. So yes, it still goes up. You can see this, maybe a bit less than the black. So it is going, the carbonyl goes up, but not as high as this. And it's flattened. Same thing with crossover, it goes down, but not as bad as this. And then it flattens. So if I can stop this change, if I can stop it to be flattened forever, that means I stop aging, at least in terms of rheology. So I say my material is stopped here and it's gonna continue forever going that way. What does that mean in terms of actual chemical functional group? Here is AFM-IR. We published this paper in case here, in case you want to check details. But look at this green and red curve here. You can see they are not the same because one is the green is on the surface and the red is the total binder bulk. We all know that the surface ages differently than the bulk. So if I cut this thin layer on the top, which is aged, underneath it is not as bad. On the top is that bad, but as I go lower and lower inside, it's not as bad. And this figure literally shows that. You can see the peaks here and here are very different between green and red and black, which shows there are variation in depth profile in aging. So what if I can stop the aging on the top? It's fine if I get the top layer look like this, but if underneath is perfectly awesome binder, no aging, then I'm good. So maybe another approach is stop the aging on the top. Don't let it go through. And there are methods to do that. So I'll tell you a bit about those. These are again back to biomass. That is one of the methods we are using. This paper just came out last week. We're talking about some of the biomass like pine, walnut, all of these are familiar to you, like peanut shell. Think of peanut shell. We eat peanut all the time. These are peanut shells that gives us a lot of phenols. And phenol-rich bio-oils I get from this. And keep that in mind, these are biomass. So the CO2 from air went into this biomass sequester. Now I'm getting this oil from it. So phenol-rich bio-oils are very strong antioxidant. So if I can reduce the oxidation phenomena on even on the top layer, if I can block it right there and protect the bottom layer, that could be a benefit. So in this paper, we actually showed that addition of phenol-rich bio-oil reduced aging significantly. So it worked, and the mechanism of it is how the phenol donate hydrogen and as a result reduce the oxidation and agglomeration. But I'll show you what happens if we add some carrier to that. So stopping 1 second here, these phenol-rich oils needs to be dispersed in asphalt to be able to work. You can't just put it in a corner. It has to be everywhere. So what we did here, we use a carrier for it, which is funny in a sense that I'm not advocating plastics production, but plastic now is everywhere, right? We talk about waste plastic being so problematic and so forth. Some of those plastic I'm showing you here are recyclable, some are not. And in this case, we actually use PET for one scenario as a carrier for oil, and we attached our bio oil onto the plastic and then dispersed it into the entire asphalt. I'll show you the results. So the method of making those plastics are easy to make. You can follow this, paper that we published on plastic. These are mixed plastic that made from bottle or shampoo bottle, whatever is mixed. And then we treat them to become this middle picture is PET grafted by bio oil. And then it absorbs some of the asphalt molecules like hexagon, benzoic acid on the surface of it. This is just a DFT calculation. I'm not going to go too much on the chemistry side, but we show that how the biomolecules can actually attract and absorb asphalt molecules. On the left are the asphalt molecules we picked. On the right is the PET plastic molecules that are interacting with asphalt. And this work was published here in this paper. But overall, what you see on the top is aging. I just showed you the aging change over time. So look at the x-axis is 200 hours. If it's a neat Arizona asphalt, it's the yellow. Look at how the aging change. Carbonyl index is an indicator of oxidation. Sulfoxide index is another one with oxygen bonds to asphalt. So as the aging progress, that's what we expect. Oxygen bonds and the yellow bars keep going up and up and up. If I continue beyond 200 hours, it still keeps going up. What we have done with this oil grafted PET is the green one. We just distributed those inside our asphalt and measured the same indicator. You can see the green is significantly lower than the yellow bars all the way. So maybe that would be a way to reduce aging. And on the a caveat on the side is, we always talk about plastic being non-biodegradable. It doesn't go away. It lasts 100 years and so forth. Well, if that's durable, if that is that durable, maybe we can take advantage of it right here if it doesn't go away. So maybe I can use it as a sacrificing agent or a molecule that can prevent aging. Solution number 2 is not that the aging happened to some extent. And I showed you here, even with the green, the aging happens, right? The green is still going up. It doesn't go as high as yellow, but it's still going up. So some level of aging happens, even with our best case scenario, best case solution of number 1. So maybe we should combine solution number 1 with solution number 2 to have a synergy. And the solution number 2 is continuously add rejuvenator and make sure your asphalt stays as good. And here is a good picture of it. If the road is getting this cracked surface, what if I can turn it back to look like this? And as it gets aged, I keep reversing it or rejuvenate it. If I do that in a quick enough interval, maybe I don't get to those potholes. Maybe I don't get to that significant crack. So rejuvenation is another way of extending the life. And here I'm telling you, why do I need rejuvenator? Well, because many of the properties of asphalt degrading with aging. I showed you how the cracks happen, how the look gets uglier and more, aged. But look at this indicator as healing index. Asphalt is supposed to have some healing ability. If it tiny cracks, it can heal itself. Sort of like your skin, you get a scratch, it heals itself. Asphalt can have some healing capacity, but over the aging time, up to 100 hours, you can see the healing capacity drops almost to nothing. So it was initially high, but as it aged, keeps dropping to nothing. So if I wait enough, like I wait 100 for this aging healing to reach to this point, I would call that asphalt dead. And I call that critical aging point. If you wait too long to get to the critical aging point, you don't have a chance to make it alive. Like if I'm dead, you can't bring me back. But if I'm sick, you can make me feel better, right? You can improve it. So the same thing, if the asphalt got sick here, maybe we can help. But if it's dead all the way here, sorry, too late. And here is the rejuvenator proof of it. We added this rejuvenator, very effective. You can see in some scenarios, it does pretty good job. But as it gets to like this end of healing, I can't bounce it back. It's just too late. The healing of too low, it won't be restored. Maybe it improved a bit, but it's not enough to reduce cracking. I proved that with Glover row parameter. Many of you know this, but even if you don't know, as we move toward the left in this curve, left and up, it's getting worse and worse. So remember, left and up, it's getting worse. And you can see from the 20 hours aged material to 100 hours, we're all the way up here. Which one of these is more prone to crack? We have this threshold. So if the dots are within the threshold or below this dash line, that's good. As it gets above this, severe cracking happens. Here, onset of the cracking. So we want to be as low and to the right as possible in this curve, at least. So these are the age one. You can see the 100 hours is way past to severe cracking. Let's see if I can reverse it with rejuvenator. I add the best rejuvenator we have found so far. You can see they shift a bit, but the one that was 100-hour age didn't even move. It's right there. This one with the circle around it didn't move. Well, the one, the 20 hours one, I could move it. See that triangle now is low, but the one that is severely aged, like 80 hours one, there's no hope. 100 hours one, no hope. So you have to watch what is critical aging point to make sure that your asphalt doesn't die out. And in terms of properties of asphalt, this is also very familiar. If you get a new asphalt, touch it with your hand, just with your finger. You feel the freshness and the compliance of that. That's the test that it shows. So when I touch a brand new asphalt, which is the, well, it's not as brand new, but it's 20-hour age. So 20-hour age is black line. If you touch it with a force of 0.01, you can indent it this much, which is sort of like when you touch a sample with your finger, you can change the, deform it to some extent. But think of this. If I do the same amount of force in a 50-hour or 100-hour aged one, which is red and green, I barely get half of that indentation, which is expected. It gets aged. But now with rejuvenation, I want to go back, right? I want to improve those properties. Here is a series of rejuvenator we found in the market, and A to L, we acronym. We of course we don't disclose the brand name or commercial name, but you look at this rejuvenator. Supposedly, this is my unaged, all the way to the right. This is the blue is aged, all the way to the left. Obviously, when you say I want to go from aged to become unaged, you are moving toward that. Most of this care rejuvenator, they help you move toward unaged. But the caveat here is, look at this violet one, for instance, or even this blue. It moves a bit, but it doesn't even change the slope. It's as steep as the aged one. All of these rejuvenator are tested with different parameters, and only these 3 within this circle were the ones that are successfully rejuvenate. The rest of them are just softening. So when you soften things, still move toward unaged, the curves move, but they're not rejuvenating, they're softening. So among all of this, imagine they're being sold as rejuvenator, only 3 of them are rejuvenating. How would I know what is rejuvenating? When asphalt age, they become agglomerate, they oxidize, they bundle. So this is the picture of XRD that shows the peak move toward the left, but in a simple schematic, you're gonna get a bundle of asphalt molecules agglomerated, and that's aged. There's a picture on the energy wise. So when you have 2 unaged asphalt, the energy of interacting is 44. As soon as they become a bit oxidized, become 48. That means they're gonna attach like magnets, more and more and more. So if you get more of this layer attached to each other, what happens? You're gonna get these large agglomerates that happens on the left. And you don't want that, because all those bad things I just told you, that's because of those agglomerates. So we have to break the agglomerates. If a rejuvenator truly rejuvenates, it should be able to diffuse into this agglomerate and break them apart. Reduce the agglomeration size. And here, for instance, from this big one in a schematic, you can get these tinier ones, and you reversing a bit of the bad effects, but not chemically. I'm not taking away the oxygen that is already bonded to them. I'm just physically changing the conformation of molecules so that they are not stacked in a different way. And so this BR or rejuvenator can get the energy also reduced. You can see from 48, now we are back to -15, which is the bonding of those. They're not gonna agglomerate as much because we got bio rejuvenator in between. Same thing with this. So a bit more on the DFT side, but the overall message is biorejuvenator can get within the agglomerate and break them apart. Weakening effect is critical for a rejuvenator to work. If it cannot get inside, look at this rejuvenator. If it cannot get inside to push these two away, it would be just around it and like a liquid flowing around your asphaltene agglomerates. This molecular modeling shows you how this whole thing works in a sense of different molecules. So I just showed you this molecule, for instance, gets in, this one gets in, but some of the alkane, for instance, doesn't. That's how it helps us to formulate a rejuvenator that has maximum effect, because we got rid of the ones that cannot diffuse and added those that can diffuse into the agglomerates. Here in the 4:1 ratio, we did many different scenarios, and this has a combination of protein and lipid. I don't want to go to the biology side of things, but we managed to create this, which this paper made it to the cover page of ACS journal, is talking about if you can get a combination of protein and lipid, you can make a rejuvenator which is highly efficient, because all those molecules can diffuse in and break aggregates. In that sense, you actually know we have the science and the tools to make the rejuvenator the way we want. So, and if we can get those from biomass, which happen to sequester carbon from the air, now you are killing two birds with one stone, because your rejuvenator is effective. And by the way, you actually sequester carbon from the atmosphere into those. So this is the algae that I was telling you. So this algae made from carbon sequester from the air and combined with the waste from animals, carcasses, anything that gives you protein can be combined with this. So the recipe was a breakthrough where we have a patent pending technology on this, because now we don't have to limit with one source of biomass. As long as you can get a combination, the right combination, we call it balanced feedstock of protein and lipid, you can get the most effective rejuvenator made for the aggregation of asphalt, at least. And this is just a picture of how this whole thing works. Rejuvenators connect to the asphaltene, get inside, break them apart. You can see in the last one, they are de-agglomerating. And that's the definition of rejuvenator. I'm going to stop here and see if anyone has a question. This has been a passion in our group for quite some time. We'll be happy to talk about it more.
Wonderful, wonderful, wonderful. I simply think you have done a fabulous job, Ellie, conveying a pretty complex topic in very simple and understandable manner. I hope that I see a lot of known faces and some unknown. They have a lot of questions. I know I have questions, but I would actually open the floor for questions. So if you are asking a question, please unmute yourself and then talk. And then when you are through, then if you please mute it again, so that there would not be any unwanted feedback. So with that, we open the floor for questions. I know Red Clark has yes, Red, please.
Ellie, hi, thank you for that presentation. It was very interesting. Ellie, we are working with processes that introduce unreacted rubber into asphalt mixes, allowing the rubber to commingle and to interact with the binder during the mix production process itself. And in doing so, we're sequestering some of the lighter ends that you've been referencing as part of this rejuvenation model you're developing. We are observing in the field in many pavements, we've been doing this for 20 years, we're observing in the field that our pavements are not oxidizing as fast as a standard hot mix pavement would in similar circumstances. And in fact, we've got side-by-side comparisons showing that. And I'm wondering whether the sequestration that we see, which pulls the lighter ends into the crumb rubber itself, is duplicating some of the elements of your work by limiting the amount of loss that you see from the asphalt, or whether we are seeing the effects of a different set of antioxidants coming from the tire rubber itself into the mix during the mix production process. And I wonder if you could comment on that.
Raymond, this is a great question. When we talk about rubberized asphalt, every road almost in Arizona is rubberized asphalt. Rubber has this magic that you mentioned, and it has both effect you mentioned. So in my opinion, we have done some work on rubber as well. I think rubber works as a temporary carrier or release agent for those light compounds. So it delayed the aging over time for a few reasons, but one of those being the light compounds belong to asphalt, as I mentioned. They don't belong to the air. When you initially adsorb them to the rubber, they will release on demand when the asphalt gets aged and it needs it right then. So there is this dynamics between rubber and asphalt. In our, just simple-minded looking at it, we think, okay, the rubber adsorb and sitting there. Well, as the asphalt age, those molecules that are light can come back out. So there is this dynamics of keeping the light compounds from evaporating, which rubber helps. Rubber has a lot of silica and carbon black that helps with blocking aging effect. Both benefits are there when you manage to, properly get it into the asphalt and combine and so forth. One caveat with the introduction of rubber in asphalt is always problems that may be associated with, incompatibility, I would say, that can lead to either call it phase separation in my term or segregation in a larger sense. If that can be taken care of, I think rubber is a definite good solution for asphalt, and you see those a lot. Some states, I know in Carolina and others, I've been there, they had issues with application of rubber, but as long as you can get it in and make a nice road of it, the benefit is right there. Good point. Both effects of delaying aging is there, volatilization and anti-aging effect.
Yeah, I would just one quick follow-up, and that is that the whole point of these dry process additions into asphalt mixes is to avoid the sort of separation process that has plagued the industry after the iced tea evolution in the 1990s with rubber and asphalt. So I think, again, your comments are right on the mark. We get the uniform mixing in the asphalt mix, and I think you're now describing better than I've heard before, some explanations about why the rubber is giving us extended life in the roads. Thank you.
Excellent. Thank you, Red. We have a question from a chemist, Ellie, and so Mr. Kabir, please proceed.
Yes, my name is Kabir Golam, and I'm the chief chemist of a refinery. We make asphalt, so we produce asphalt. So my question is, I just got the last part of your presentation, and my question is, if you mix peanut shells or other items you mentioned, does that reduce volatile compounds emission?
That's also a very good question. So there is, well, first of all, let me clarify for everybody who's listening, none of these biomass are added directly into asphalt. They are all converted to oil, which look like very much the same as asphalt when you start with. They have different, viscosity and so forth, but these are oil, not the biomass directly. But you have a very good point on each of these biomass. They have different, obviously, molecules. So if you put them into the mass TGA, thermographic analysis, to see how much it loses over temperature, they have variation. So in case of peanut, actually the loss is pretty low. We measure their density and as it changed over aging, as well as the loss. So some of the biomass have created some misconception over the years in our industry, which maybe I should correct it right here, is that we look at carbonyl index as a point of aging, as a tracker for aging. Many of these bio-oils, they are high in carbonyl to begin with. That's part of their molecules. If they have structures that CO double bond is right there, you can penalize them for giving you a high carbonyl index after you measure it. This is right there in their structure. So many of the papers you may see in in industry, there's this misconception that biomaterial have higher aging rate because carbonyl is higher. That's not true. And in terms of the biomass loss, if you start with a very low boiling point or low, high volatile material, you will get more loss, which is something to actually work in all of these biomass when you start using bio oil. Because if you think about it, crude oil been underground for many years, it's been going through evolution. So many of those volatiles are already converted to heavier molecules. Bio oil, we just made it in the lab in 20 minutes. So instead of millions of years waiting, we make it accelerated and it's 20 minutes to 1 hour. So this has a lot of volatiles. And trapping them, and that's another caveat I didn't mention, when you trap it with rubber or plastic, in this case, we use PET, some of those volatiles are combined and they're not gonna run away. We showed very good interaction there. But that's something you brought up, very, very good point. It has to be watched when you use any of low molecular weight substances to add to asphalt, which has already very high molecular weight. So those light molecules could evaporate at our temperature, mixing temperature, which then come back to this point that, well, we want to get away from high temperature to begin with. So maybe instead of heating our future asphalt to 150, 180, maybe we can get away with lower temperature to minimize the loss in a secondary manner. But first manner is bond them to your entities, whether it's rubber thermosets, like Redmond mentioned, as rubber, or PET, which is thermoplastic, as I mentioned. Make sure it's bonded so it doesn't run away. Great question. Thank you.
Excellent. Thank you. I think I'm going to say that we will not end at 11:30, which is Oklahoma time, Central time, LA, if it's okay, because there are a couple of additional questions. So I hope that that's okay with you.
Absolutely.
So let's finish those questions. So my colleague, Dr. Paul Huang, has some questions for you.
Hi, Dr. Fini, thank you very much. This is really excellent talk. We'll get you back and probably give us a talk here in the chemical engineering department.
Yes.
Sometime soon. So
I'll be happy to.
Yeah, for the past 2 years, me, myself, with my colleague Ed O'Reilly here, we have been really working with Professor Zaman, and we try to understand also as a role of the waste cooking oil when we try to use this as the rejuvenator, so on. So we really share lots of common interests. So my two quick questions would be in the second part, you mentioned about the model of the aggregate. So what is the model of those aggregates? Are you more talking about separating the S14 aggregates, or it's quite complicated of the overall aggregate?
That's a very good question. First of all, thank you for Dr. Zaman to pull you into our domain. I told my student always, when you get to asphalt, it's sticky, so be careful of what Dr. Zaman is getting you into. So you're gonna stick around with asphalt for a long time to come. But
yes, I'm already here.
Yeah, it happened to me the same way. So thinking about those aggregates, first of all, let me clarify for everybody who's listening, he's not talking about the stone aggregates, stone minerals that we talk about. He's talking about the agglomerates or aggregates of asphaltene molecules when they bundle and self-assemble into a so-called nano aggregates. So this is a very good question, starting with asphaltene, because right now there are so many controversy on how asphaltene even look, because it's not like we can dig in and look at them, right? This is such a complex matrix, and that's the beauty of it. We have 10 to the power of whatever 6, 7 molecules in asphalt, and among asphaltene there is archipelagy, there is island model, there are many different suggestions on how asphaltene look like. So we use the model that started way back with Zhang and Greenfield's model, and then we modified it. When I was at MIT, we modified it to become more stable. Our argument is asphalt molecules being underground for millions of years, they cannot be those molecules that can evolve too easily. So we made it even more stable. So that's one of my papers that says modified Zhang molecule. So I started using now that molecule. But as for the aggregation, we managed to calculate with DFT the pi stacking interaction and how the oxidation happens. We did not
model oxidation phenomena itself using Reacts FF or any of those force field.
Yeah.
We basically use the highest potential points to oxidize, and then made the oxidized version of asphaltene from a virgin asphaltene. These are the model side. And then from that point on is just to run a molecular dynamic simulation with PCFF force field to see how many aggregates and how large of an aggregate we get. And then the reverse is when we can get the rejuvenator to diffuse into it. We saw that the interaction energy between asphaltene can be reduced, but on the MD side, we managed to calculate the average size of agglomerates to see they are reducing. And then corresponding to that is, of course, when you talk to folks in our field, they are not chemists, so be cautious what you talk to us, different vocabulary. So we bring it back into rheology sense. So all those breakage of agglomerates, my civil engineers don't want to touch that, right? So we connect that to rheology, and the crossover modulus and crossover frequency showed a very good connection with agglomerates. As the aging happens, aggregates get larger, crossover modulus drops. As we can reverse the aggregate size to be a smaller, crossover modulus bumps back. And that's how we differentiate between good and bad rejuvenator. And then it turns out in the field, when you do all this balance mix design and all this, it also proves. But we didn't start from mix design to see if it works or not and walk back way. We actually started from bottom up approach, as you know what I mean. So we figured out which molecules can break down, increase crossover the highest, and then synthesize that using balanced feedstock of protein and lipid.
Excellent, excellent, excellent. So for the interest of time, I'll save my next question when you come back for another visit.
Excellent. Yeah. So okay, wonderful. That's a good thing. Anybody else has any questions?
I have a
Yes,
question.
Dr.
Like, if we have, I have a question, like a very quick question, maybe. Thank you for this presentation, Dr. Fini, and I really enjoyed every bit of it. Actually, this is a great presentation. Thank you. One question is that, like, a kind of like applicability side. Actually, two questions here. First of all, you said like you are using PET HDPE as a carrier for your rejuvenator and then release it inside. Also, you're saying like so using PET or HDPE, that type of like a little bit heavy molecule, we have found that like there are some issues with distributing and distributing the those binders, those molecules inside asphalt binder. For example, like there are some settling issues and other stuff that they do not melt properly and goes inside properly. So like how do you manage that? Because as you mentioned, like all the PET molecules has to be distributed or in all phases of asphalt, otherwise it may not work. This is one question, and another question is that like
I think let us wait there and let us answer that. And
Sure.
in the interest of time, I think it will be nice if you ask your question just briefly, so that yeah, that would probably allow more questions. Yes, Ellie.
So this is a good question. Let me answer it in a way that when I showed you the all the plastic table, that was a purpose, that plastics like human, they have names and they are different. So when we talk about PET, it's very different from LDPE and HDPE and PVC. We managed to get PET, which is I guess higher melting point, grafted with biomolecules. So think of that approach as more of what Redmond was talking about, the rubber. We're not mixing at the molecular level, but if this PET is grafted with these biomolecules around it, now it works as a magnet. Using magnet as an analogy, obviously. Magnet for the asphalt molecules, volatile molecules. So we showed that some of the volatiles that are actually quite not healthy, like benzothiophene, for instance, or benzoic dibenzothiophene is one of them. Benzoic acid, another one. Hexanol is another one. Those, they actually attach to this magnet which we made. If you just add PET right there with asphalt, it's not even compatible. Its phase separate pretty bad. If you do a cigar tube, it's like arm and a leg. It's very different. But when you actually graft it with biomolecules, the biomolecules attached to this, it works as a bridge to keep those volatiles, and they mix well in asphalt. We were not successful as much with HDPE. So let me put it that way.
Excellent. Thank you.
Thank you. Minister.
What's your second question, Ashik, briefly?
So yeah, my second question was related to that. Like if we are doing biografting, how feasible is that for application wise, like in the plant and stuff? So that was my second question.
That's also a very good question. So you may already heard that there is a road in Missouri, there is another road in California in use plastic, and we just did one in Arizona. So plastic is making its way to asphalt anyway. The problem with many of those plastic is incompatibility. So if we can pre-treat those plastic, because if they want to be successful with asphalt, they have to compatibilize it. So the word compatibilizing means post-treatment. If that post-treatment can be combined with biografting or use biografting as compatibilizer, then there is an additional steps as you already mentioned, but then it will be compatible. Plus, it will get the volatiles also stay in. If you just use whatever surfactant or compatibilizer, it may not actually keep the volatile, or it may not add antioxidants, right? So here we are adding something that compatibilize and add antioxidant. So we haven't done cost analysis. That's a very good point in terms of scaling, but technically it has a merit. Yeah. I don't know if it's economically viable.
Excellent, thank you. Any other questions from anybody else? Any other questions from anybody else? Well, I want to just close this by really thanking you, Ellie, for an excellent, outstanding job in presenting a very complex topic in a very understandable way. So I agree with Paul that we'd like to have you in person and have another, more in-depth discussions. So this has so much science, so much application and new horizon. There will be a road in future that will never age, and there will be ways that we can actually make our road not only carbon neutral but carbon negative, as you indicated. So also I want to let you know that a PDF of our presentation will be added to our SPTC website, as well as our recording. So if you have to go back and just review what she presented, I think that would be another opportunity to do so. Paul, you want to say something, or?
No, I just want to say that thank you again. So I really learned and enjoyed lots of nice features from your presentation. So.
Yeah, excellent. There was one, I think, Sai Krishna. I'm sorry, I just did not see your hands. I think I want to make sure that nobody is ignored here. Everybody has equal importance. So, Sai, you want to have a question for Ellie? Yeah, you raised your hand. Well, I think so. Anyway, so we're a little bit over time, about 10 minutes our allocated time. So please give Ellie a round of applause, and we look forward to seeing her in person. Thank you very much, and thanks to all of you for your attendance. Because and also please let us know if you want to have another topic that need to be covered. We would make sure that that is done. So wonderful job. You have a great day. Thank you all.
Thank you.
Thank you.